Okay, so welcome back. So let's go ahead and start creating a model just like we looked at. And because of that previous video, you should have a lot better understanding of what's going on here. So let's go back to our code, and we're going to import a couple of things, and then we're going to build this. So we're going to say from Keras, import sequential, and from Keras, import layers. This might be Keras.model, actually. .models import sequential, I think, is correct there. So what we're going to be importing is a sequential model. So this is a group of layers, like we just talked about, essentially. And then this layers API, this is going to let us create different types of layers. So for example, if I do layers dot, you could see convolution. You can see that there's convolution 1D, 2D, 3D. So that's where we can select the type of layer that we want to use. So let's go down and let's jump over to our code, and let's create a new function. Let's call this gen model. So this is the code that's going to generate our model, and we'll come back and figure out what we need to pass in to do that. So the first thing we want to do is we want to create a model object. So we're going to call Keras. Oops, we're going to say model equals sequential, because we already imported that. And we're going to provide a list of layers, and the layers are going to come in the form of a list, a Python list object. So this is where we're going to add all of our layers one by one by one. And if you remember, if I go back to the previous graphic we looked at, this is our input layer. So this is our pixel data that we're going to have to, let me grab my pen here. We're going to have to scale between 0 and 255. We're going to want to scale that to a value of 0 to 1. And then we're going to want to go ahead and create these other layers here, the hidden layers, until finally we get to an output layer. So we're going to do those. We're going to put those in a list one by one, and that's going to tell Keras how our model should be built. So the first thing we're going to do is we're going to build a normalization layer. And again, the normalization layer is there to take the data, the RGB data that's in a range of 0 to 255, and scale it to a value of 0 to 1. So we're going to go ahead and say the first item here is going to be layers dot layer dot let's see, rescale. That's what it is. So layers dot rescaling, and we're going to put in our scale factor. So our scale factor is going to be 1.0 divided by 255.0. So we're going to divide by 255, since the maximum value in a 0 to 255 range is 255. That will force everything to 0 to 1. And then we want to put in our input shape. So we'll say input shape equals, we'll call this shape. We'll define a parameter when we generate the model. We'll call a shape here. And that should be it for our first layer. So let me actually, no reason to make this more than one line. That can easily fit on one line. Let's clean this up a little bit. Just like that. So this is our first layer. Our first layer is we are going to take all the data that comes in, and we are going to rescale it to, by dividing it by 255. That's the first layer in our model. And then we just do comma, and we're going to keep adding layers, which are all inside of this list object. Okay, so our next layer is going to be, let's go back to the tutorial, and let's start with what they have. So they also have a rescale layer, and then they're going to do some convolutions. So they're going to do 3 convolutions and 3 max pooling, which is what we talked about in the previous. So this is going to be a convolution operation, and then this will be a pooling operation. So now that you understand what that is, we can easily implement that as well. So we're going to call layers.layer, or sorry, layers.conv2d. So we're going to do our 2D convolution. And then we're going to put in some parameters. So we're going to enter the number of filters, which you can kind of think of as the number of outputs that we want. So we'll get 16 out. and we're the kernel size, so we'll say 3, so this will be a 3 by 3 window. And then let's have padding equals the same. We talked about the padding. And then activation, which is something we didn't talk about, but essentially activation is a function that will determine if a node is turned on or turned off. And you can imagine if you have a button, buttons might have different levels of resistance. So a button that you press very lightly might suddenly activate. A button you might need to be pushed very hard. You can kind of think of this as a function that basically turns that node on and off. And the ReLU is a specific type of function. So let me just show you what that looks like. All right, we'll come back to that. I'm having an internet issue. So next we want to do our max pooling. So we'll do layers dot max pooling. Oops. Layers dot max pooling 2D. And we'll enter that layer. And then we're going to add another convolution layer. So we'll say layers dot conv 2D. And this time we'll do 32 filters. We'll do 3 padding equals same, activation equals ReLU, and we'll do pooling again, layers dot max pool 2D, and finally we'll do the third convolution layer. So we'll do layers dot conv 2D, and this time it's 64, 3 padding equals same, activation equals ReLU. Okay, so those are all of our convolution operations. Convolution, pool, convolution, pool, convolution, and I'm missing the last pool, so we'll do layers.pool 2D, not average pool, max, we're going to do a max pool 2D. And now you can see how easy this is to understand. A average pool would take the average value and pool that, so that's pretty intuitive as well. So we're going to do the max pool 2D. And then, so if we go back to our visual graphics, so this is where we kind of are at now in our model construction. We've built so we have our normalization layers, we've done our pooling and convolution. Now we're going to add a dense layer. So if we go back to the example, they have a flatten and dense layer, and then finally they have a dense layer that's based on the number of classes. And what this is essentially going to do for us is it's going to take all this data and it's going to create a dense layer, like I said, which is basically one node is connected to every downstream node. So all these nodes here are going to be connected to these downstream nodes here. So these guys are going to connect to every one of these guys. And then finally they have a dense layer at the end that's based on the size of our outputs. And that makes sense because we want a dense layer at the end to correspond to each type of result. So this might be Rose, this might be Daisy. So we want that final layer to be of the exact same size so that when the model thinks it's a Rose, that lights up. When the model thinks it's a Daisy, that one lights up. So those are the last sets of layers in our model. So let's erase that and let's go back. So we're going to do a flatten operation here. Layers.flatten, layers.dense. So we're going to create a dense layer here, and let's see how many units did they use. They used 128, so they have 128 nodes. And they're using the same activation, the ReLU function, which I'll describe in a moment. And then we're going to take that, so we're going to have a dense layer, of a certain size, of a size 128 actually. So they have a layer that looks just like this. But instead of only 4, they have 128. So that's what that is. There's 128 of these from top to bottom. And then those are going to feed into our final layer. Just imagine this goes away here. This would be our final layer. This is our output. And this is going to be the same size as our output, as I mentioned, because we want each of these to correspond to one thing, like rows, for example. So let me go back. So that's 128, and then we're going to do another dense layer here. And we're going to correspond that to the size of our, I'll just hard code it in. It'd be better to put a variable here, but we have 5 classifications, I believe. Let me check that. 1, 2, 3, 4, 5. Yeah, we have 5 types of flowers. So we are going to define that as 5. And activation will be ReLU. Okay. So essentially this is the model right here. And then of course we want to return this model from this function because we're going to generate it and return it. So essentially this is the model right here. Our model is a sequential model. It starts by rescaling, or you can think of it as normalizing the data. We have 3 convolution and pooling operations, which we talked about, which are these types of operations here. Convolution, pool, convolution, pool, convolution, pool. Then we take those outputs and we flatten, and then we go into a dense layer, which is basically a certain number of nodes. In this case, it's 128 nodes, and all of them are densely connected to the output layer. And the output layer is the same size as our classification. So we have rose here, daisy, tulip, or whatever. So that is the whole model. So that's what we've just built essentially in code, very easily with Keras. And that's basically all there is to it. It's very straightforward. And if you wanted to add another convolution layer, that could be done very easily by just taking these here and duplicating them and modifying the parameters accordingly. So very easy to build a model and add layers and remove layers and modify layers. That's what's very powerful about Keras. So let me just explain really quickly this ReLU before I end today's video, which is actually quite significant. So the ReLU is an activation function, and it's basically like a hockey stick. You can think of it. I'm trying to open this page here. So this is a good example of what a ReLU function is. So imagine we had a function that had a value from between, let's say, -1 and 1. Well, if we just had a linear line, that would mean that when it's -1, the value is negative. When the value is 1, it's positive, and when it's in the middle, it's 0, obviously. So just imagine a straight line. Well, if that's what we were using to activate a node, that could be a little bit tricky, because imagine a node is like a button, and you want to determine, is that button pressed? Well, you might have a range from, let's say, 0 to 1 or -1 to 1, and you might say below this value, and in this case it's 0, we want you to treat the output as 0. And then above that value, we want to have a certain output. So this causes that node to basically not be turned on until it reaches a certain activation threshold. That's why it's called an activation function. And there are other ones other than the ReLU. So another one is like the sigmoid function. So let me show what a sigmoid activation function would look like. So you can see here's an example of a sigmoid where from a negative to positive, it swings from 0 to 1, just like the hockey stick does, except where this one is kind of transient and smooth, and the hockey stick one basically goes from 0 to, it ramps up very quickly to 1. So it's more of a step change, like on and off, versus the sigmoid, which is kind of smooth. So there's different types of activation functions, and that basically determines how this layer will be activated. How much input gets you how much output activated. Do you want this thing to kind of be triggered on and off, or do you want it to be kind of a smooth, linear relationship? So that's what those activation functions mean. So in the next video, we're going to go ahead and build the model. Now that we've created the model, we have to build it and actually compile it, if you will. So see you in the next video.